Good day again, ladies and gentlemen, and we are back together. All right, so today I just wanted to do a question on work, energy, and power, and this I took from the Gauteng paper, the Prelim, just to help you to just diagnose, and see how well you did. And obviously, I can do this even for other provinces. Yeah, we'll see how it goes as we keep doing our revision. Keep revising. Please just make sure that you work hard and please don't break that momentum, right? Okay, so please, for those of you who haven't subscribed, please make sure that you become part of the family, right? And welcome to the new subscribers. And by the way, we've dished out quite a lot of lessons. If you're struggling with any part in your physical science, there are lots and lots and lots of lessons that you can actually benefit from. And for those of you who just need help, with tutoring and all of that, right? Please just send me an email on info@mlungisinkosi.co.za. Okay, let's get right into it. Okay, they say we've got a 2 kg trolley which is at rest. Okay, this has to do with work, energy, and power, or energy principles. Right, so our trolley is at rest. Okay, so there's our trolley over there on a frictionless surface. They tell us that a constant horizontal force of 8 newtons is then applied. So we know we've got an applied force there. And they said to the trolley over a distance of 3 meters. So we're going to apply that force over that entire distance over there. Okay, so now they say at point A in the diagram, the force is removed. So we remove the force there. The trolley moves up, okay, a distance of 7 meters, okay, up the incline until it reaches a maximum height at point B. Now, just something to note there. When something is moving on its own, right? So in this case, the only reason why it was still moving is because it was still carrying a momentum from being pushed or pulled, right? So what then happens is that it will continue, but it will be slowing down until at maximum height. Now, what happens at maximum height? It means that in this case, this trolley would actually stop at that point. Okay, that's very important to consider. All right, so now they say to us, okay, they say the trolley moves up a distance of 7 meters up the incline until it reaches maximum height at point B over there. They say the trolley experiences a constant frictional force of 1.5 newtons while moving up the incline. Okay, right, now we are dealing with two different surfaces here. So if we were to call that, let me just call it from the beginning up until that point A there, they did tell us that it's frictionless, right? So there was only that applied force that was acting on it. Okay, now they say to us define a constant horizontal define a non-conservative force. What am I reading? Define a non-conservative force. Remember, we say non-conservative force, these are forces whose work done, right, depends on the part taken. So you can think about forces that never remain constant, nor do they actually stay or remain in the same direction, like frictional force, for instance, right? It's a non-conservative force, right? These are forces whose work done does not depend, rather depends on the part taken, right? So they say draw a labeled free body diagram indicating all forces acting on the trolley as it moves along the horizontal surface. So in this case, look, they've given you three marks there. So it means they're expecting three forces. So what's going to be that force? First of all, you're going to have that applied force there. Okay, so I'm going to say, well, this is force applied. Okay, but which other force do we have? We've got gravitational force, or you can say the weight, but it's also moving on that surface there. so we actually will have the normal force. Okay, so that's going to be a normal force over there, right? And essentially those are all our forces, right? Right, so they say state the work energy theorem in words. Okay, I'm not going to write that down, but remember it simply says the net work done on an object is equal to the change in kinetic energy. And by the way, please note that the moment they ask you to state a particular theorem, there are greater chances that you are going to have to use it in the next question, right? So this was our 5.2. So 5.3, you're going to state it there. Okay, so that's 5.4. Okay, they say use energy principles to calculate the speed of the trolley when it reaches point A, right? So they want us to use energy principles over there. Okay, so I can use my the work energy theorem. It says the net work done is equal to the change in kinetic energy, and I'm going to find the speed over there, right? Now, what is my net work done? Remember the net work done, we say, well, in this case it's going to be F net. And why am I doing this? Because I want the speed that's associated with this guy, so I'm going to have to find the net work done somehow, right? So I'm going to say, well, this is F net, so work done, that's force times displacement, the cos of the of angle theta, right? So F net cos delta x cos of theta, which is equals to EK final minus EK initial, right? Remember that this trolley is moving, it was at rest initially, so it tells us that our kinetic energy initial is 0. Now let's talk about that net force. Remember, these two are vertical, and they are balanced, so their net force is, the net result is 0. But this trolley is moving in the horizontal. So which are the forces that are acting horizontally? Of course, it's the applied force, right? So in this case, I'm going to consider direction of motion. And I did say to you, ladies and gents, by the way, to those of you who have no clue what I'm talking about, please go and watch our, that's our most watched video on work energy and power. Please go and indulge over there, right? So we say, well, F net, in this case, that's our applied force. We know the value of F net, that's going to be 8, multiplied by, what's the displacement? They said it's 3 meters, so that's 3 meters. The cos of, now, remember we said, what is this angle theta? This is the angle between direction of motion of the object, right, and the force in question. So in this case, it's the angle between direction of motion. So where is this trolley moving? It's moving in that direction. And the force that we are talking about in the question, it's also in the same direction, right? So if the force is in the same direction, the motion is in the same direction, what's the angle between them? Of course, that angle would be 0. So this would be the cos of 0 degrees, right? This is equal to, so that's half the mass. Our mass was, okay, the mass of the trolley is 2 kgs, so that's 2 times the final velocity squared, right, which is what we're looking for. And remember, the kinetic energy initial was actually 0, right, because our initial velocity was 0. Okay, and all that's left for us is just to do a couple of gymnastics mathematically, right? So what do we get there? So that's 8 times 3 cos of 0. Okay, so this is 24. Okay, divided by a half of 2 is 1. Okay, and we take the square root. So this is going to essentially be the square root of 24. And I simply get 4.9. Okay, so VF would be 4.9 meters per second. Okay, right, and you can calculate that for yourself. All right, let's go to the next question. They say calculate, they said use energy principles to calculate the height, that the trolley reaches at point B. Right, now please, I want you to note the moment it goes up the incline, what are the forces that are going to be acting? Well, we know, well, in fact, that's incorrect. So in this case, it's going to be frictional force that acts there. Okay, so that's going to be kinetic friction. It's going to be gravitational force. Okay, and please note it's acting vertically downwards. So this is Fg. Okay, and it's going to be our normal force. Remember, the normal force is perpendicular to the incline. Please, can you ignore this? And by the way, they didn't ask you to draw a free body diagram. I'm just being extra generous, just to show you guys what should be done for this question, right? And by the way, just something very noteworthy. Note, we could have drawn the free body diagram this way, and that's kinetic, that's normal. But instead of having that gravitational force, I can have the components of gravity. So I can have the perpendicular component, Fg perpendicular, and I have the parallel component. And remember, this always acts down the incline. So this would be Fg parallel over there. Okay, right. And the advantage of having these like that, because now you know that your normal force would actually be in a straight line with your perpendicular component of gravity, right? Just as an additional, just as a reminder, remember, how do we get that Fg perpendicular? We always say mg, the cos of angle theta, right? In this case, we're not given angle theta. I'm going to show you how we'll answer that. So as well as Fg parallel, we always say this is mg, the sine of theta, where in this case theta is the angle of elevation over there, right? Now, I haven't answered the question. I haven't even started, right? It's just showing you how those free body diagrams. Remember, this is revision, so we're kind of dancing around just to see how to approach certain things, right? So they wanted the height there. Now, whenever I do not have an angle and I am given, or either I want vertical height, I wouldn't go the network done route. So what I do is I'll go work done by non-conservative forces is equal to change in kinetic energy plus the change in potential energy, right? Now, please, I want you to note, we know the velocity there, okay? It's the one that we calculated that side. We got 4.9 meters per second, okay? But we also know the velocity there, okay, right at the top, it's going to be 0, right? Now, then you may ask me, what's the work done by non-conservative forces? And ladies and gents, please, I don't want you to complicate your lives. The moment you see non-conservative forces, just think two forces only. That is the force applied as well as the frictional force. Okay, those are our non-conservative forces. Of course, we can talk about others, but in particular, when it comes to questions here, it will be those two forces, right? Now, I want you to note which are our non-conservative forces. So that means that Fg parallel and perpendicular don't form part of our non-conservative forces. Why? Because gravity is a conservative force, so it means its components are also conservative. Why do we say it's a conservative force? Because force of gravity does not depend on the path taken. It's always acting vertically downwards, right? So I'm going to say, well, it means it's the work done by the applied force. But what do you know? As it was moving up, is there an applied force? No. So it means that the work done by applied force is 0. And the work done by frictional force. And do we have friction as it goes up? Of course we do. They said it's the friction is 1.5 newtons, right? Okay, so this is going to be EK final minus EK initial. So that's, in fact, we can even say kinetic energy at B minus kinetic energy at A plus potential energy at B. Remember, it's the change in, so that's final minus initial, minus the potential energy at A. Right, now let's substitute everything that we know. Remember, work done by applied force, that's 0. Okay, I'm just doing that for emphasis, by the way, just to show you. I could have just written work done by frictional force, right? Now, how do I get work done by friction? This is going to be friction multiplied by delta x, the cos of angle theta. Okay, right, we'll come back to that once again. Right, kinetic energy final, remember at B we said it stops over there, so this is going to be 0. Kinetic energy at A, okay, so it's going to be, we said our velocity is 4.9, right? So this is going to be half of 2 times 4.9 squared, okay, plus, okay, potential energy at B, okay, so our potential energy at B, remember, this is mass times gravitational acceleration times height. Remember, that's potential energy. So our mass is 2 times 9.8 multiplied by that height there, right? That vertical height. But in this case, what's our potential energy at A? It's also 0 because the trolley was not elevated above the ground. Okay, right. So in this case, what do we have? We've got friction, which is 1.5. Please, very, very important, times, we know it was displaced 7 meters, right, up the incline. The cos of, what's our angle? Now, once again, we said when we use this work done principle, this angle here, please remember, ladies and gents, it's not the angle of elevation there. We said it's the angle between direction of motion. So there's our motion, it's going up, and the force in question. Where's friction moving? It's opposing, so it's going down the incline. So what's the angle between them? Up the incline, that's my motion, direction of motion. Force in question is acting down, so the angle between them is 180. So in this case, this would be 180 there. Okay, right. I don't know why I'm using a different color. Okay, so I guess, yeah, it's for emphasis, ne? Okay, so this is going to be, we're going to do our gymnastics over there. This will be 4.9 squared. Okay, which gives us 24, right? And then plus 2 times 9.8, this is 19.6 H. Okay, and all that you need to do, ladies and gents, is just obviously gymnastics. So I'm going to have, right, so that's 1.5 times 7 cos of 180. Okay, and then, so if, oh, by the way, I almost committed an error there. Remember, this would be negative, right? So if I take this to the other side, it becomes positive. Okay, so this will be plus 24. Okay, and right, I get 13.5 if I take that to the other side with that, and you divide by 19.6. I'm sure you can see how it's going to unfold. I get a height of 0.69 meters. You can verify that for me, ladies and gents, and tell me if you get to the same answer. All right, and this is basically how you are going to treat it. Okay, I'm sure you by now, for those of you who have watched my video on this, and some of you have been reporting that, hey, you are getting incredible results, because of watching these videos, and I'm sure it will be the same for the final. I'm sure what I've tried to prove is that, you know, it's really not impossible to do well in science. Okay. Please just keep watching the videos and practicing and working hard. Okay. Right. We are almost there, and I'm sure you guys will make us proud. And please, when you get those results, hey, come back and post and you know, tell us how incredibly you did. Okay. Right. Otherwise, I'll see you guys again next time. All right. Don't forget to subscribe. Sharp, sharp.